Hi everybody, welcome back. This problem, this example right here is probably going to be our first real good application of taking component forces, or taking an object and looking at their component forces. So we have a force of 20 newtons right here that's being applied to box 1. Right? It has a certain mass, 10 kilograms. So it's being applied to box 1, but we're being told that box 2 is moving as well. Now you know that if you have a box right here and a box right next to it and they're touching each other, if you push the one box, they both will move. That's just kind of what we observe and what we sort of accept. But why is box 2 moving right here? You're really not applying a force to box 2. Well, you say, well, because box 1 is pushing, or box 1 is moving, so therefore 2 has to move. That's true, but what's probably more accurate is to say, and I kind of said this, that box 1 is pushing it. That is, box 1 is applying a force to box 2. So this force that you are applying from the outside, this 20 Newton force, part of it is going to accelerate box 1, and part of it is going to accelerate box 2, that is through box 1. Or that is, part of this force is being applied through box 1 to box 2. All right, so I'd like to kind of let's see, fix this up a little bit. We have our masses of our boxes, 10 kilograms and 5 kilograms, and our 20 Newton outside force. All right. In fact, let's go ahead and call that our net force of our system. All right. So I'm going to make that in red, I think. Okay. The net force on the system equals 20 newtons. Okay. So if we were to take both of these boxes as a system, so pretending that they're just one great big kind of oddly shaped box like that, this force would be the force that is applied to the whole 15 kilogram system that would cause it to accelerate. All right. But we can also take each of these boxes and look at them individually. All right, I'm going to make one box blue. So this guy right here, this first one I'm going to make blue, and the second one I'm going to make green. Now let's see here. Yeah, I can make it. Now I'll make it the same old green. All right, green right there. And let's relabel these forces. Now, if you recall in the I'm trying to think of the canoe problem, sorry. What's the force that existed between the person's hand and the adjacent canoe? Well, we called it the contact force, right? So this force, the force that exists in this surface right here, is really what is causing this second box to move. You can think of it as a whole giant system, or you can think of it as individual boxes. If you think of it as individual boxes, then really the force that is causing this box to move is the contact force that exists between the two boxes right here, and it's really this force that's coming through box 1. So let's change this notation a little bit. We're going to call this force from 1 to 2. All right, force from 1 to 2 right there. All right. So yes, it is the force on box 2, but it's a force from box 1 to box 2. All right, and similarly, we're going to change the name of the force that's being applied. The contact force is being applied back to box 1 as force 2 to 1. All right, so box 2 is applying kind of a resisting force back to box 1 in this contact force right here. All right, so these are both going to be the same, but as you see, we wrote the subscripts opposite. They're going to be equal in magnitude, but opposite in direction. Okay, so let me take this whole thing, and I'm going to shrink it down a little bit. So do this, like so. So we've got different component forces acting on each box. All right, the box 1 right here has this outside force, this whole 20 Newton force acting on it, but it also has this kind of contact force or resisting force pushing back on it from box 2. Box 2 only has this contact force coming from box 1 on it right here. So we have different component forces acting on each box. But one thing that we can say is true of each box is that each box is going to have the same acceleration. Let's look at it first as a system. Let me move this up in the corner a little bit more. There we go. As a system, and I'll do this in red, okay, for the system of two boxes, we can say that here's our mass, all right, our two-box mass, and it has a mass of 15 kilograms, okay? Mass of the system equals 15 kilograms, and I'll draw the floor right there. And we have this 20 Newton force being applied to it from the outside, okay? Force, the net force on the system equals 20 newtons. Sorry, my writing is so lousy. So what we can say is that for this whole system, what is going to be the same between both of these two different boxes, if we think of them as a whole system, is that they're both going to have exactly the same acceleration. All right, we can say that the net force on the system, is going to equal the mass of the system times the acceleration of the system. Okay? So if we can find this acceleration right here, we're going to find that each box has that acceleration because they're both part of the system. They're both moving with the same acceleration. All right? By the way, I've been sort of showing you bits and pieces of this problem right here. Let's just read it real quick and find out what we're being asked to find. I think I already just told you what the first thing is that we're asked to find. A box with mass 10 kilograms is box 1. Rests on a smooth horizontal surface, so we're assuming that there's no friction. Okay, smooth horizontal. Next to a box of mass 2, which is 5 kilograms. This guy right here. If you push on box 1 with a horizontal force of magnitude 20 newtons, that's this outside force right here. What is the acceleration of the boxes? So we want to find the acceleration of the system, which is the acceleration of each of the boxes individually as well. Okay. For part B, which I may just make into a separate video, we want to find the contact force between the two boxes. It depends on how much space I take up with this right here, but it may or may not be a separate video, so we'll go on and see how long it takes, okay? So let's find the acceleration of the system right here, of the boxes collectively. All right, well, that shouldn't be too hard. By the way, where do we get this from? This is Newton's second law, all right? So we can say that the acceleration of the system is going to be the net force on the system divided by the mass of the system. All right, what's the net force in the system? It's not the only force, but it's the net force. The net force is this outside force right here of 20 newtons. You might say, well, what about these guys right here? Well, first of all, they're not an outside force. And even if we do account for them, the contact force, we said, Newton's third law says that any contact force produces an equal yet opposite in direction reaction force. So if we were to take each of these forces, one thing that we can assume is that they are equal yet opposite. So they would cancel out anyway. So really, the only net force on the system is this outside 20 Newton force. All right? So that's our 20 newtons right there. 20 newtons divided by the mass of the system. Well, that's 10 kilograms plus 5 kilograms, right? So that's 15.0 kilograms. What does that come out to for the acceleration of the system? 20, what's that, 1 point, I don't need my calculator, I think. 1 and a third, right? 1.333. 1.33 meters per second squared. That is our acceleration of the system because we have the net force on the system, 20 newtons, and we have our mass of the system, which is 15 kilograms. Okay, so that's our acceleration of the system. I think we should be able to do part B in this segment as well. What is the force of contact between the two boxes? Okay, so let's do that in black. All right. So this part was part A right here. Part B, what is the contact force between the two systems. So F1 to 2 or F2 to 1. That's what we're solving for for part B. All right. So we actually have a choice. All right. Since Newton's third law tells us that these two forces right here are equal yet opposite, we should be able to solve for either one of them. All right, because they are equal. We're going to assume, well, we already have assumed that this direction right here is positive, and therefore the opposite direction is negative. So if we were to solve for the contact force pushing back on box 1, we would have to say, okay, that's in the negative direction. But I think this is really, part B is just asking us, what is the magnitude of the force of contact between the two boxes? Because, of course, they are pointing different directions. So we've got a choice. We can go with box 1 right here. All right? We can solve for that contact force, the contact force between the two boxes, using box 1. All right? Box 1 is going to look like this. It's going to have, and I'll put a 1 right in the middle there. It's going to have a 20 Newton force on the outside. I'm just going to put 20 newtons. Now, of course, box 1 is 10 kilograms, right? I'll put a little 1 right here and make this 1 into 10 kilograms with a 20 Newton force going that way. But it also has a force coming from box 2. I made that one blue, I think. Yeah. Coming from box 2. We called that, this was the contact force from box 2 being applied to box 1. All right? So that's what box 1 looks like. It has this outside force, but also this contact force from box 2 being pushed back on it. Box 2 is actually, we're going to find, a little bit simpler. Now again, we could use either one, but let's use what's simpler. Box 2 is going to look like this. Okay, it's long and flat. There's our 2 right there. It is 5 kilograms in mass. I'll draw my bottom line right here. There's that. There's that. And it only has one force being applied to it, and that is a force from box 1. Force from 1 being applied to 2. Okay? So, these two forces here, this one and this one, are equal yet opposite, so we want to find out the magnitude of them. Which of these two boxes would be easier, do you think, to use to find that contact force? Well, box 2, right? Because for box 2, we have the mass, and we know the acceleration of that box because it's the acceleration of the system. We should easily be able to solve for the force of contact that's coming from box 1 to cause that box 2 to accelerate. All right? You don't have to use box 2, but it certainly looks like it'll be simpler because this has more forces acting on it. This only has one right here. So we're going to say for force from 1 being applied to box 2, which, by the way, that's also going to be in the positive direction, too, so that should make that simpler. Okay? We can say acceleration of box 2 is going to be the acceleration of the system, right? It can't be accelerating faster or slower than box 1, and that's going to be our 1.33 meters per second squared. Okay? The force from box 1 being applied to box 2, that's the question mark right here that we want to solve. And we know the mass of box 2, and that's 5.0 kilograms. Okay? So, Newton's second law tells us that the net force on box 2 is going to be the mass of box 2 times the acceleration of box 2. I think we should be able to find that net force. In this case, the net force on box 2, is the only force on box 2, and that is that force from box 1. All right? So we can say, all right, well, those are saying the same thing. They are equal. And so we can say the force from box 1 to box 2 is going to be the mass of box 2 times the acceleration of box 2. Let's just plug in our values, and we'll have our force that's being applied between the two boxes that we call the contact force. All right? Mass of box 2 is 5.0 kilograms. Acceleration of box 2 is 1.33 meters per second squared. You can see I'm not really observing significant figures right here. I'll have to excuse that. And I will need to get my calculator for this. I'm not going to do that in my head, but be a little bit faster. 5 times 1.33. I get 6.65 newtons. And that is our contact force. So that contact force is being applied to box 2, from box 1. It's also the force that force 2 is pushing back on box 1, because box 1 is going to feel that same force just in the opposite direction. All right, so this really is the contact force between the two boxes, equal in magnitude but opposite in direction. All right, there we have it. So that's example 5-6. Good use of Newton's third law, equal yet opposite forces, and Newton's second law, of course, which is net force being equal to mass times acceleration. Okay, that's going to be all for this example. Thanks for following along. I'll see you on the next one.